preferred language for the presentations is English. I can fake a little bit of Portuguese, but it really sucks. So I guess you are going to get the version of the talk that results from the translator. Trying to buy some time as an introduction about myself. I've been working mostly in security assessment of communication protocols for about 10 years or so. During that period of time, I've worked for a couple of government organizations in the UK. And then essentially I started my own company to do the same kind of stuff. This presentation is going to be about IPv6 security. What I have tried to do for this talk is try to summarize the stuff, the new stuff that has been produced in the last, let's say, 1 or 2 years. My previous presentation at H2HC was in 2012. So what I tried to do was to give you, for those that at the time were present at that presentation, try to provide an update of the things that have been produced in the area of IPv6 security so far. Much of the work that I do, or part of the work that I do, is at the standards organization that is the IETF. That's the organization that standardizes internet protocols. So part of the stuff that I will be discussing are protocol updates that we have generated to improve this the state of affairs of IPv6 security. At the same time, there's other stuff that I do, such as coding tools. I have authored one of the, let's say, few toolkits that there are out there for playing with IPv6. It's an open source tool. So the second part of the presentation will essentially try to focus on the toolkit, on the practical stuff. Let's say. For some time, so this might need to get interrupted. Funny, no, or not that funny part is that I was dumb enough to update to the last release of Ubuntu, like 1 day ago or so, and apparently there are some things with the video driver, not just this, but also with VirtualBox, that it's not working as expected. So I guess I didn't follow the if it's working, don't touch it. I didn't touch it and it's not working. Okay, let's see. Whatever. So, as I said before, even OpenOffice apparently has been updated. So it's just showing something here that I've never seen. So I have like a chronometer here showing how much time I guess I spend on trying to fix the display stuff. This presentation, as I said before, is about IPv6 security. And what I tried to do was to provide a summary of what are the things that changed, let's say, since the last 1 year or last couple of years. This is a very brief introduction about myself that I already mentioned. This is my, current job. This is what I've done, in the area so far. I participate a lot at the IETF. At the IETF, I author a few RFCs on IPv6. Other of that stuff is ongoing work, which means that it's stuff that eventually will get published as RFCs. Other than that, I also try to do some practical stuff. To the extent that is possible, I try to do what I call the full cycle. Try to do analysis, find problems in the spec, implement tools to break that stuff and so on. And this is kind of like my 2 previous employers. I added an introduction because that's what people usually do. But from my perspective, you shouldn't care about that. I'm of the idea that if the stuff that I'm presenting, it's nice, I mean, you should like it and enjoy it. And if not, no matter what I did before, I mean, it sucks. What is the motivation for this presentation? If you look back, as I said before, I have been working on security assessment of communications protocol for a while. And before doing V6 stuff, I was doing the same kind of work, but on other protocols. And if you look at, let's say, TCP and IPv4, which are the protocols that predate IPv6, if you want, and you try to put your mind in the 90s, essentially in the 90s you had all these now well-known vulnerabilities such as SIM flood attacks, predictable sequence numbers, etc., etc. If you do some analysis on how things evolved in the IPv4 era, Essentially, there were people finding ways to exploit the protocols, and kind of like after the fact, people were trying to produce fixes for those problems. So you'd see protocols being exploited in the wild, then patches applied to implementations, and to a large extent, the work of the community was kind of like reactive. So they were trying to fix stuff once they found that those things were being exploited. So the motivation of the work that I do is, you probably have seen this movie, is try to save time rather than just sit on the table, wait for stuff to be exploited, and then try to produce fixes. Try to save time. Try to implement these fixes in IPv6, fix the standards, fix the implementations, and so on. So that we can do more of a, let's say, proactive work in terms of V6 security as opposed to reactive stuff. As I said before, during this presentation, we'll have essentially two parts. The first part is mostly, let's say, standards stuff, theoretical stuff. The other part is practical. Stuff that I will not cover on this presentation, and this is in relation with some, let's say, bets and jokes that we did with Rodrigo. I'm not going to make any jokes about the World Cup for many reasons. Now the reason is that I spent like about 10, 15 minutes getting the projector to work, right? So I'm not very much in the position of making jokes. So we won't talk about that. I'm not about that either. This one I got from a Brazilian friend. I didn't know what it was, Connie. But apparently this guy is one of the coolest guys in the world. I mean, he got to see the World Cup from the field and without doing anything, right? We had this guy, Messi, which didn't help us much, so we don't have that much to say. But as you say, yeah, we were this close of winning the World Cup in Brazil. That would have been like huge for us, and I guess not that good for our team, because I think that all of them would get dead before getting back into our country. What is the main V6 security problem? So this is a slide that I did not even work on the graphic myself, but I tried to analyze, well, what's the problem with V6 security? What's the worst stuff? And what I say is that probably the worst problem with V6 security is that there's so much crap that gets published and that people repeat without even checking whether there's any fact about that or not. This is how you could put it. There are lots of myths going around there have been myths going around for ages. V6 being more secure because it supports IPsec, etc., etc., etc. There's also the thing that everyone has something to say. I mean, that's like, it's free, I guess. And as I said before, people repeat everything. So this is one that I came up recently, which, people usually state that this is supposed to be the information area, but from my perspective, it's the communications area. So you have all these communications means, you have Twitter, Facebook, and everything, but I don't know to what extent what circulates over there is information, or just people, forwarding stuff just because they can. The outcome of that is that there's, so much crap going on that if you are, let's say, new to this stuff, or if you just don't focus on this stuff, it's hard to tell, what's true from what is not. And that's where, you get confused, and that's where the field doesn't evolve that much. So first part of the presentation will be about protocol issues. What I did is I just selected a subset of the stuff that we could discuss. Among other reasons, because this is stuff that is so specific. I spend like hours and hours a day just keeping track, of specs and changes. So if you don't focus on this, there are stuff that if I, get into details, you will probably don't understand much, but not because it's difficult. It's just because you need to spend time on it. So the first topic that I will briefly discuss is V6 addressing, and this is an overview. I'm not going to get into the usual, V6 introductory stuff that you usually hear. So this is like a one-slide review. This is the syntax of V6 global addresses. And if you think about it, it's essentially the same thing as in IPv4. Just you have a global routing prefix, some bits for subnetting, and then you have an interface ID, which is what in the IPv4 world you used to call the host ID. But it's essentially the same thing. Probably the main difference here is that in V6, that interface ID is 64 bits long wide, which means that you have more options on what to do with those bits than in the IPv4 case, where you only have typically, let's say, 8 bits, and you just, increment that value. For several different reasons, which I'm not going to focus that much here, there are different, let's say, techniques or algorithms to set the interface ID, like the host ID part, and these are some of them. One of them, which is called the auto-configuration way, is you essentially just put your MAC address in the interface ID. That's what you will usually find if you are, running any system that supports V6. You can also put your IPv4 address in there. Even the V6 address notation supports that. So if you check this one, if you check the second bullet, you can check that there is a V4 address embedded in the V6 address. Of course, what happens in that case is like you compress those 4 bytes into the low order 34 bits of the address. Other things to do is just do something similar to what you do in, in V4, set the thing all to zeros and you just vary the last byte. Wordy addresses, people, just come up with words based on the fact that, V6 addresses can be expressed in hexadecimal. The most, let's say, most common example is Facebook. So if you obtain the V6 address for, www.facebook.com, you will see that the interface ID is Facebook. There are some transition technologies, stuff that is used to, try to make V4 and V6 interoperate that essentially tells you how to set those bits. And the final one, I think, is some random addresses that have been used by Windows for a while. So Windows decided to move away from the traditional way of selecting the interface ID. Oops, here we go. And final one, it's random and temporary addresses. These addresses are sometimes referred to as privacy addresses, and we will see later why they refer to these addresses as such. So let's just mention briefly what are the security implications of V6 addressing. To some extent, you could argue that the main change from V4 to V6 is the addressing architecture, or the fact that the addresses are larger. So that's why this could be like an important topic. So among the security implications is that you can correlate network activity over time. And the idea here is simple. If you have an address that is so large and you can put in the interface ID a value that is, let's say, globally unique, as long as, let's say you are a web server, as long as you always see the same address, you know that it's the same system that is connecting to your server. That's something that, to some extent, didn't exist in V4, not because V4 was better or prettier, but because of the fact that, for example, in V4 you have things such as network address translators. So you have many devices hiding behind the same address. There is another implication, which is probably worse than the first one, which is the ability of correlating network activity across networks. The idea is simple. Just let's assume for a second that the way in which you set the interface ID is you put your MAC address there. The MAC address is supposed to be globally unique. If you take 2 interface cards from any vendor, the MAC address is supposed to be globally unique. So if you put that value in the interface ID, that value gets seen by whoever you connect to. And let's say if you are, for example, a web server, and first of all you see a connection from the first address, 2001, DB8, blah, 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 blah. I have put in bold the interface ID part, which is just an ugly number. And then sometime later, you see a connection from the second address, FC00 and blah, blah, blah. You can check that the interface ID is the same. So, I mean, since it's a 64-bit long number, which is supposed to be globally unique, that's kind of like, embedding a serial number in your IP address. And that means that it's easy to track, the activity of a node across networks just because of how they generate the V6 addresses. Other stuff is what you could call address scanning. In IPv4 is kind of like straightforward because the address space is so small that you don't even need to think about it. You just go through the whole address space. For example, if you want to scan an organization, you just need to know what's the prefix that is being used or employed by that organization, and you just vary from all zeros to, let's say, 255 or whatever that is. In V6, things are different because since the addresses are so large, the brute force approach doesn't work that good. But these are of the implications. And the final one, which is kind of like related to what I discussed before, is the ability to, at times, perform device-specific attacks. So if for some reason you knew that some kind of device was vulnerable, some hardware device was vulnerable to some specific exploit, in this case, since one of the techniques is to put your MAC address on the interface ID itself, just by looking at the IPv6 address, you can tell what's the device that is connecting to you. The only one that I will cover of this, because that's the one about which more crap has been circulating for years, and you actually still hear that stuff, is that of address scanning. This is a quote that I got from Google when I was trying to find out what people were saying about this stuff. And the stuff that you can usually hear about V6 address scanning is that it is virtually impossible. And the numbers vary from one person to another, but this one is 500 million years. So the idea here is that if you were to scan a V6 network, well, it would take you forever. Probably not even the planet Earth would be there for you to complete this. But, you know, when you read this kind of stuff, there's like, let's say, two possible different options. So the first one is that probably the guy that did this statement was just on drugs, right? So it's crap, which is the reason for which I included the image. But I tried to consider the other possible option, which was like, well, maybe this guy thought about this problem in some different way. So I tried to come up with what could be going on in his head while he was, you know, doing this kind of statement. And I guess that the only, you know, possible option that I came up with was that these people were assuming that when you are scanning a V6 network, you need to go through the whole 64-bit long space, where you can, you know, select all of your host addresses. In the bottom of this slide, you can find a document. That's a file name, draft, ITF, OPSEC, blah, 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 where we discuss this stuff in detail. But this is just a reference. But, you know, summing things up, when we were, you know, working on this stuff, in part at the ITF, I said, well, what can we do to actually have some kind of, you know, real-world experiment to check whether, you know, V6 address scans do take that long or not? And what I came up with was this. I came up with this idea. So I said, well, why don't we just, you know, measure how addresses are generated in the real world and check if they follow any kind of pattern. So what I did is I employed two different sets of domain names. One is from Alexa, which last time that I checked, I think they don't publish it anymore, or I wasn't able to find it that quickly. And the other one is from the World IPv6 launch date. It's www, I think it's World IPv6 launch date altogether, .org or something like that, which contains a list of specific sites that were enabling IPv6  2 years ago or so. What I did in this case was obtain V6 addresses for all of these domain names. But, you know, since I have the list of domains, I say, well, let's check if maybe they select addresses differently for, let's say, mail servers or, let's say, name servers. So what I did is also grab the domain name, get NS records, and then get the IPv6 addresses. Grab the MX records, and then get the V6 addresses. These are the results. So there are the reason for which for the web you have all these four charts is that on one hand you have one chart for the Alexa dataset, the other chart for the World IPv6 launch date dataset. But also what I did is I removed duplicate addresses. So that's why you have, you know, 4 graphics as opposed to 2. I think that the important part here is that when you look at the chart and you can easily tell that this, you know, light blue thing is low byte addresses, you can easily tell that addresses do follow patterns. It doesn't really matter that much which pattern they follow, but they do follow patterns. This is the distribution for web. This is for mail servers, which you can see at the bottom that if you target the low byte addresses, you target more than 90% of the addresses. This is the same thing for name servers. Again, I mean, you can analyze the details. I think we actually wrote something on this, but I think that the important part is that the addresses do follow patterns. The outcome of this is that, you know, address scans are possible. It's just that you need to do your work a little bit smarter than the way in which you do it in IPv4. Sadly enough, when you look at the usual tools that you use for address scanning, most of them have rather poor B6 support. So, for example, well, without naming names, but among the popular scanning tools, not that many years ago, they did not even support the slash notation. So you couldn't even scan some prefix that you wanted to scan. But I guess at this point in time, the implications are understood. So now let's talk a bit about what are the possible ways to mitigate this stuff. As I said before, I work both on tools that do the attack part, but I also do the defense part, which means trying to fix this. One of the, let's say, techniques that had been around for longer is what they typically call temporary addresses or privacy addresses. And this, let's say, this scheme or this algorithm is specifying RFC 4941. The idea is pretty simple. You have your traditional IPv6 addresses, which you generate, for example, by putting your MAC address there, but you also have these temporary addresses, which, as the name implies, are temporary, and they are random, too. So the idea is that you select a random address, and you change that address over time. The idea is that you will use these addresses, these temporary addresses, for outgoing connections. So if you are connecting, for example, with a web server, and let's say you connect once, you connect to the server now, and then you connect again, let's say in 10 hours, well, chances are that your address has changed because, again, these addresses are temporary. So even if the web server tries to analyze your address, since the interface ID is random, there's not much that it can infer from that. Unfortunately, as with many mitigations, there are problems too. So let's say that you are running a network, and for some reason you are meaning to run your network in a similar way as you used to do with IPv4. In IPv4, it's not that unusual that you find that this system with IP address, let's say 1234, has become infected and is sending packets to here or there. And when you realize about that, and when you look at the address, you know what's the device that is using that address, so you can disconnect the device, reinstall it, or whatever. Now, in B6, if you are using these temporary addresses, and these addresses, let's say, intentionally change over time, that means that if you have some, let's say, some entry in one of your log files that says that, the system using address 12 blah, 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 was, sending packets or was attacking other systems, let's say, 4 hours ago, well, that address is probably gone. So it's hard to manage these addresses, and that's the reason for which in many networks where B6 is deployed, these temporary addresses are disabled. Another problem with this is that these addresses are used in addition to the traditional addresses. So let's say if you were using the traditional B6 addresses that include a MAC address, then you use these ones in addition to those. That means that you still have the addresses that are predictable. And that means that even if you implement RFC 4941, you are not mitigating scanning attacks. The predictable addresses are still there. The only thing for which this is to some extent useful is to try to conceal your identity when you move around a network and you connect, for example, to a server. What we did to fix this problem is essentially to produce something that replaces the traditional way of generating B6 addresses. This is a simple expression that we use for that. Let's say the simple way to analyze this is that you will generate the host ID or the interface ID part as a result of a hash function that is computed over a prefix, which is whatever prefix you are supposed to use for your network. And let's just say, for the time being, just the prefix and the secret key, okay? So you come up with a number as a result of running, as a result of running the hash function over the prefix and the secret key. Of course, if the secret key is secret, even if you know the prefix, you don't know what's the outcome or what's the result of the hash function. So this is just, a longer explanation of, this. There are a few other parameters that you include in the hash function. For example, you include a counter, because if you are extremely unlucky, and let's say that there are two systems that end up generating, for example, they just selected the same secret key, and they end up, generating the same address, well, that would lead to an address collision scenario, right? So you want to be able to recover from that. So the idea is that if things fail, and if the address that you generated is not unique in your network, well, then you would increment the counter that you have here, and then you'd produce a new one. But, conceptually speaking, the details, they don't matter that much. The goal, again, is just compute a hash function over the prefix and a secret key. What's the let's say the goal or the idea behind this? Of course, if it's a hash function and as long as the parameters that you are using are stable, the result will be stable. So let's say that I connect to this network, I compute the hash, and I obtain this address, let's say 1234. Now I move to another network. The prefix, of course, has changed because I have moved to a different network. Now I could get the address ABCD. Now I move back to the first network, as I was before, and then I will get exactly the same address that I was using when I was connected to the first network. So the idea is simple. As long as you're connected to the same network, you have to get always the same address. Because from a management or network operations point of view, that's interesting. But when you move from one network to another, you want the address to change. And that's what we achieve by using the expression that we were using before. From the point of view of your local network, it looks like the address, your addresses don't change. But as you move, the addresses do change. There is a FreeBSD implementation. As far as I recall, they now enable this by default, but I have not double-checked. And I do know that there is a Linux implementation in the works. But the nice part of this is that it's not just a document that was published for the fun of it, but it's something that is actually reflecting into real implementations. Now, you may know that in V6 there are two ways of configuring addresses. So there's the auto-configuration thing that I was referring to before, and there's DHCP version 6, which is kind of like V6 version of DHCP. There have been cases of DHCP servers where they lease incremental addresses. So when they get the same request from the first request from a client, they assign the address all zeros and 1. Then for the next one, they assign the all zeros and 2, and so on. Once people found that that was not like the best possible option, because again, that would lead to predictable addresses that are easy to scan, some DHCP servers resorted to generating random addresses. But what's the problem with that? For example, if you are running two DHCP servers on the same network, for example, for redundancy purposes, then if you get the address from one of the servers, you get one address. If you get an address from the other server, you get a different address. And again, we want addresses to be stable within the same network. So this is why we produce this document, which is essentially a DHCP version 6 port of the expression that I was using before. The only difference is that in the previous case, is your own system the one that is computing the address, the one that is generating the address. Whereas in this case, it's the DHCP server that computes this value. So the idea is essentially the same. There's a prefix that you're going to use, for. There's a client DUID, which is a number that is supposed to be unique for each client. And there's this third value, I think it was internet address identification or something like that, which is, let's say, it's a value that is supposed to be constant for each of your network interface cards. So you have, to some extent, some way of detecting the client and also which of its interface cards it's trying to configure. So what the server does is essentially whenever it receives a lease request, it computes this value and then offers the V6 address to the client. What is the, let's say, the nice outcome of this? Is that, first of all, you can have as many DHCP servers as you want running on the same network, and as long as you use the same configuration parameters, such as prefix and secret key, each of those servers will handle the same addresses. So you can easily implement redundancy and achieve at the same time address stability. There's no need to share state among the DHCP servers, because it's just the algorithm that leads to the same addresses being generated. Just as a side note, the IETF is currently working on an algorithm for DHCP servers to communicate their lease information, which leads to more complex stuff. You need a new protocol, you need an implementation, and so on. But with this, it's just a simple algorithm for generating the addresses, and you don't need to rely on a new protocol or whatever. If you have let's say, a file with a list of the leases that have been, been done for clients, and that file gets corrupted, you don't really care, because it's the algorithm itself the one that computes the values. This is very recent stuff. It was adopted by the relevant IETF working group last month. So that's, as I said before, very recent stuff. Other work that is happening right now at the IETF is essentially these two documents. If you wonder why there are so many documents on the same topics, why so many separate documents on the same topic, political reasons. So essentially we have a standard on how to generate the address, but there's no one that tells you, well, that's the way in which you should do the addresses. So then you have these other two documents. The first one just discusses the security implications. The second one tells you, well, from now on, you should generate your addresses in this way. The idea is that for some implementations, that could be the case right now, but for others, let's say in a year or maybe in a couple of years, you'll find that the way in which they generate B6 addresses is different from what you are used to right now. And from the B6 point of view, that's a big change. Some comment on B6 extension headers. This is probably one of the most, let's say, boring and frustrating topics. And the reason for that is that usually the same stuff gets repeated over and over and over and over again. So what I try to do is just summarize that. First, theory. Before, when the way in which you use options is essentially you have a variable length header in which you include as many options as you want. In B6, the structure of the packets is different. It follows like a daisy chain structure. So you have the fixed header, as many extension headers as you want, and then the payload. So this is just an example. Having a fixed header, then two destination options headers, and then the payload, which in this case is a TCP segment. Fragmentation, in a similar way, is achieved with an extension header. So if you want to fragment a packet, you need to have the fixed B6 header, a fragment header, and then the fragment that you want to send over the network. So this example could be just an example of a B6 fragmented packet. The concept is essentially the same as in before. You just change a little bit the way in which you do it. What's the reality of B6 extension headers? Well, the reality is that you can get into ugly cases such as this one, in which in the top packet, you have a packet that includes two destination options headers, and then the payload, which is a TCP segment. And what an attacker could do, for example, is say, well, I'm going to send this packet, but fragmented. So the second and third packet is essentially the first one, but just fragmented. And things can get very ugly because you can, for example, as in this case, fragment the packet, but in the middle of the extension headers. So you don't even get the full headers in the first fragment. You just get a chunk of the packet. And of course, if you have some, let's say, stateless device, for example, a router that wants to enforce an ACL based on the source and destination addresses and source and destination ports, it's impossible to do it. Because you get the first fragment, there's nothing to look into. You get the second one, well, the information is there, but you don't know where to find that information. So it's ugly. And there are other problems. Many B6 implementations, for reasons that, I guess vendors should comment on that, they implement some of the B6 functionality in software, which means that you might have this expensive box that, can do B4 packet forwarding very, very fast. But now, if you try to make them forward a B6 packet, for example, after enforcing some ACL, they do the inspection and the processing in software, which means that let's say the rate, the forwarding rate that you might get with these boxes could be totally different. Of course, as soon as you do the processing in software, that opens the door to denial of service attacks, because an attacker could just fire packets so that you spend your CPU on processing that stuff. Another of the things that happen in practice is that whenever you have a box like a router that it has to, let's say, enforce an ACL on a packet, what the router typically does is it receives the packet, copies a piece of the packet to like fast memory, if you want, and then does the inspection on that fast memory. Now, for obvious reasons, that memory is expensive. And many, if not most of the implementations, they have a limit on how far they can get into the packet. So if I go back to the previous slide, and let's say I have, 1,000 bytes of extension headers, maybe the box that I'm running, it could be a router, it could be a firewall, it could be whatever, or let's say a network intrusion detection system, maybe it's not able to look that deep into the packet. What happens in those cases? Well, changes from one implementation to another. Some let everything pass through, others drop the packets, varies from one to another. There's also the thing, and this is no different from before, that fragmentation itself is usually deemed as insecure. Reason for that is that, of course, that of fragment reassembly is a stateful operation. If you are a node and you receive one fragment, you have to wait for the rest of the fragments before you can reassemble them. So that is, asking for trouble. There's the well-known stuff of fragmentation being used for evasion that dates back from the 90s. We just changed the protocol, but implications are similar. And there's also the thing of bug implementations. You'd expect that people had experience with before fragmentation and reassembly, so they would get the V6 code right. Well, they didn't. So if you look at V6 implementations, many have got this stuff wrong. And many operators, they don't really have the chance of talking to the programmers and saying, well, fix this. What they realize is, well, if this is stuff that gets me into trouble, and usually I don't really need to rely on this, I will just block these packets. A result of this is that since there's so much being said about extension headers and fragmentation, and operators have heard that stuff, many of them, Google is probably the best known example, they just drop every packet that contains extension headers or fragmentation. You cannot get to Google with a packet that contains, for example, destination options. So that means that if you have some sort of protocol or application that relies on this, it's going to result in, well, it's going to break. Because if these packets are dropped, your application is going to break. There has been so much talk about this, even in ITF cycles, but, there was, at least since 1 year, a couple of years ago, there was no real-world data about the extent to which this was happening in the V6 internet. So what I did was build tools to perform measurements. And what I did was I grabbed the same data sets as before, this one from the World IPv6 launch day side, and I say, well, I will get web server addresses, I will get mail server addresses and name server addresses, and we'll send packets to those addresses and see if they get through or not. So if you see the numbers here, depending on the type of extension header, the one in blue is destination options header of 8 bytes. The other one is hop-by-hop options header of 8 bytes. The last one in yellow is a fragment header. You get different drop rates. But it can get really ugly. Like for fragmentation, you get 30% of packet drop rate, which means that if you just want to use fragmentation for any random side, well, for 30% of them, it's not going to work. But it can actually get worse, because you could say, well, maybe it's the end system that is dropping this. So for example, there's a web server is receiving fragmented traffic, and it says, well, I don't need this, so I drop it. But it's worse. What we did is try to measure where in the network these packets were being dropped. And we came up with these measurement results that show you in those cases where packets are dropped, the percentage of times where those packets are dropped by a different autonomous systems as the final one. So let's say you have a web server here, you have a transit network here, and you have some node here. Packets try to get to the final system, but they get dropped in the middle of the network. So it's not the same guy or the same company or organization that is operating the final device, but some other guy, that is providing, let's say, transit service. This means that even if you're running, for example, a web server and now you wanted to use, for example, extension headers, it's not up to you to be able to use them. You have to get some other party to let those packets go through. So these are from the World IPv6 launch day as a website dataset. Same thing from the Alexa top 1 million side. So the packet drop rate, for example, for name servers, it's over 50%. 50%. And again, this is the extent to which the drops occur at the different autonomous system. There are cases in which in 60% of the cases, the drops are happening at a different network. So what does this all mean? I mean, the implications and these results. Well, first of all, good luck with trying to use V6 extension headers for something useful. This could be taken as a message for the guys that are actually producing protocols. So it's not unusual that you see new proposals at the ITF which employ extension headers. Well, if you want them to work on the internet, you should be really lucky. And of course, you shouldn't do that. But it's also interesting of what are the implications for the let's say security community. Because it's not unusual that, when you talk about V6 security stuff, there's some guy that comes up with, these way of using extension headers to evade some sort of control. But if packets get dropped to that extent, then the scenarios in which you can really use extension headers are not that many. Maybe in 50% of the scenarios, if you just send your packets with extension headers, you won't even get to your target. So they are not that useful even from the attacker's perspective. Okay, so what are the ways in which you can, let's say, leverage the extension header for attacks? The first obvious, boring, and everything is, just put, for example, extension headers to evade firewall or filtering device. In this case, is router advertisement guard, which is like V6 version of DHCP snooping from IPv4. So what you have in the first case, I want to send a packet, and I know that there's some device that is inspecting my packet. So what I do? Well, I generate traffic that is ugly. So this is probably the worst case in which I use both extension headers and fragmentation. But for example, when it comes to Cisco's implementation of router advertisement guard, even if you just insert a simple extension header in between the V6 header and the payload, you are able to evade that device. So I say that this is all and obvious because it has been repeated over and over again for like about 2 years, so nothing new. This is stuff that I thought that it wouldn't work, but in practice it does. Which it's kind of like, it's about essentially leveraging the fact that so many networks are filtering packets with extension headers. So let's just assume, let's say that I have two systems that are communicating, this one and this one. They are sending traffic to each other, and I know that the network that is in the middle of them is dropping packets with extension headers. So the question is, well, if I know that the network is dropping the packets, maybe I could be able, what if I could be able to have one of those systems just send packets with extension headers so that somehow they cause the RAM packets to get dropped. It's easy to do that. You just need to send, I won't get into the details, but it's just an ICMP version 6 error message that you need to send, which is the equivalent to IPv4 fragmentation needed and DF bit set. Well, in IPv6 it's called packet too big, PTB, as here, which is, again, ICMP error message that claims that there is a link with an MTU smaller than 1,280 bytes. What happens once any node receives one of those packets, it starts sending what we call IPv6 atomic fragments. What's an atomic fragment? It's a packet that is not really fragmented, but it just includes a fragment header. So you have here just one packet, a fixed header, the payload, and below that you have an atomic fragment. The only difference between the original packet and the atomic fragment is that you inserted a fragment header. I won't get into the details why this was specified in this way, but the idea, let's say the conclusion is that it was a very bad idea. So what you could do with this? So let's just assume for a second that you have, let's say, a client downloaded information from some server on the internet, right? And you know that the internet at some point in the network is dropping packets with extension headers. So what you could do as an attacker is essentially send an ICMP version 6 packet too big error message to the server. That will cause the server to send from now on all of the packets with a fragment header. And since the network itself is dropping those packets, then you will get the denial of service scenario. So it's the network dropping the packets, it's not the attacker dropping the packets, but since the filtering of packets with extension header is so widespread, there are many cases in which this attack will happen. I will go through it but quickly, but one of the systems with which, I don't know why I tried with it, but if you try to get to www.kernel.org with IPv6, because it's IPv6 enabled, this is an attack that easily works there. Apparently, at least from this hotel here, there's some network, which I didn't research that, but there's some network that is dropping packets with extension headers. So again, as an attacker, you just send one ICMP version 6 error message, and from now on, the server will send packets with a fragment header, and the network itself will drop those packets. What I did to reproduce it, I will not get into it because we are probably like, more late than we could ever be. But the idea is very, very simple, and these are the commands that you should run. First of all, let's say you want to check that, B6 connectivity with that device is really working, right? So you can, for example, easily do a telnet to port 80 of the target B6 address. That's the address of www.kernel.org, okay? So what you get in that case, if everything is working as expected, you will get a connection. The connection gets established. What you do next, you just use one of the tools in the toolkit to send the ICMP error message. The idea is simple. The address that you have in red is the address of the target. The address that you have in blue is the address of the client. In my particular case, since I didn't want to attack a third party, I attacked my own connection, so to speak, but without sniffing packets or anything. I just knew my own IPv6 address. I was downloading stuff from kernel.org. I sent that packet, and after that, which I'm not going to reproduce it here, but if you check connectivity again, you just try to do telnet in the same way, you won't get any connection at all. You will get a connection timeout. Why? Well, because the error message led the target system to send you all of its packets with a fragment header, and there's someone in the network that is dropping those packets. So, game over. If you wonder, well, what's the rate at which I should send those error messages for the attack to persist? Around 1 error message every 10 minutes. That's because usually implementations cache the MTU value for 10 minutes. I mean, for legitimate cases, that's perfect. But in this case, that means that just by sending one packet every 10 minutes, you can keep that traffic flow with a denial of service. The second one, which honestly speaking I didn't try, but it can be very ugly, is lovely BGP. And why lovely BGP? Because, well, with BGP, if you are able to, get damaged there, well, it's networks that fall around. It's not just, a client to a server. So let's just imagine this scenario. And this is not just, random thoughts. It's based on, feedback from operators, if you want. Let's just say that you have these two BGP servers here, okay? Usually they are on the same link, okay? And let's just say that these servers, they are operated by security-conscious people, and they say, well, we don't need fragmentation, so we will drop fragments. And that's, interesting to some extent, so that they are not subject to, fragment floods and all those kinds of attacks. But the problem is that in many, many cases, they drop the B6 fragments, but they don't do anything to prevent an attacker from triggering the use of fragmentation. So if you go to the same example as before, which was this one, you could think of the client as one of the BGP peers, the server as the other of the BGP peers. The fact that they are connected on the same link, it doesn't really matter at all. So what you do as an attacker, you send one of your error messages, that triggers the sending of packets with, the fragment header, and if the BGP peers are dropping the IPv6 fragments, you get a denial of service attack there. Just if you wonder, because you might think, well, but in order to do this, you need to spoof your source address and blah, blah, blah. You don't. I'm not going to get into the details, but if you want, we can discuss it further later or by email. So that's the way in which you reproduce the attack. This is the outcome. Important stuff is that you may think, well, but I have this peering session that is using TCP MD5, which is a crypto option for authenticating TCP segments. Or you could be using IPsec. You say, I'm protected. No, you're not. Because your packets don't even get to the other system for the IPsec validation. The problem there is that eventually they get sent with, using B6 fragments, and when the peer receives those packets, they drop those packets even before looking what's inside. So that's something that is nice to experience. Let's say it would be politically incorrect to, try to reproduce this in the real world, but, there are the tools, so it's up to people to, reproduce this. What are the ways to mitigate this? Well, first of all, that of responding to those ICMP messages by sending fragmented traffic is a horrible idea. So the first document, that's a file name, is a document that I published a few months ago, which essentially says, change the standard, that's not a good idea. The second document, draft Gont obsec blah, 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 essentially tries to provide advice on how to filter packets with extension headers. What people are doing right now is essentially filter everything, and that's probably not the best idea. second and brief part of the talk, which is about getting dirty stuff done. Probably one of the reasons for which I included this is that I asked Rodrigo, say, well, I have defense stuff and attack stuff. What of that stuff you want? I can say, we like attack, and so that's why I put this stuff here. The nice part of this is that you can reproduce it with tools. Sometimes, when it involves just reading documents, it can be boring, and you wonder, well, I don't know if this works in practice or not. But this is stuff that you can reproduce with tools. This is a preview of the toolkit, which the plan and goal is to formally release it tomorrow. Formally speaking, within the context of the conference. And this is essentially just, a few comments on new features. So I'm not going to say what the toolkit does, because, many of the tools have been around for at least, let's say, 3 or 4 years. But this is about new stuff you can do with this toolkit. As an overview, this is a basic security toolkit that supports many different operating systems, from Linux to several BSD variants. The last one that incorporated in this new version is OpenSolaris. We also support macOS. And if you wonder, well, that's kind of like cheating, right? Because these are all Unis boxes. So no, it's painful. And even from one BSD to another, for reasons which I don't really know what they are, you have to incorporate specific code just so that the toolkit works on the different BSD variants. Not to mention OpenSolaris, which was painful. License is GPL, free software. There's a Git, so that's the home page for the toolkit, but there's also a Git repository. So if you want to keep track of the latest changes without having to track the formal releases, you can use Git. The toolkit has been incorporated into the package system of a few operating systems. So if you are using Ubuntu 14 something or Debian, I don't know what's the latest version of Debian, you can do the apt get install IPv6 toolkit and it will work. Tools that are incorporated in the toolkit, these are some of them. Many of them are tools for sending specific types of packets in whatever way you want. More tools here. And the idea is to briefly describe some new tools and scripts or features that have been incorporated into this latest version, other than the bug fixes. So one of them is, for example, I have had quite a few times, a list of domain names that for some reason I needed to, let's call, inspect, right? So you come up with the domain names, you have a list of them in a text file, and you want to get the v6 address to play with them. So nothing big. There's this tool script6 that you can, you can pipe the tool a list of domain names, and you can, ask the tool what's the kind of information about that domain name that you want. In this case, it's just about getting quad A records. Of course, you could easily implement this with your own script. This is just, a script that is included in the toolkit. You can also, for example, say, well, I want the IPv6 addresses of mail servers. So you have a list of domain names, then you pipe the output to the first instance of script6, which is about getting the MX records. That means the domain names that corresponds to the mail servers, and then you pipe that output to the another instance of script6 so that you get the addresses. And finally, one thing that you will typically find is that there are many people that enable v6 services, but they don't really know what they put there. So they can use, for example, in some cases they put link local addresses that you cannot use. In some cases they use multicast addresses for web servers, and you find all that kind of stuff. So not infrequently, you need to filter the addresses that you get. And this is something that you can do with this tool that is called address6. It has lots and lots of filtering features. In this particular case, what I'm doing is when you run the tool with a -i is to read information from standard input, and the -g means that I only want to use addresses that embed in the interface ID a MAC address. There are so many different ways in which you can do this tool. Like, I only want global unicast addresses, I only want multicast addresses, etc., etc. This was just a summary of stuff that is not, no big deal, but it's stuff that is useful when you want to play with systems. Another tool or script that we produce when we were measuring, where in the network packets were being dropped, is the ability to, to get information about the autonomous system corresponding to some specific address. So this script6 tool has an option, which is, or a command if you want, get AS, and you just give the tool an IP address, and it will tell you, well, what's the autonomous system to which that IPv6 address corresponds to. So if you, for example, you got an IPv6 address and you wonder what's the organization that is using that address, well, this simple command can tell you about that. Other stuff, and this is probably stuff that you're more interested in. So I was mentioning before that if you want to do another scan, well, you cannot just do the brute force scanning stuff that you do in before. It would take ages. For the last, let's say, easily, I'll say 2 years or so, we had a scan6 tool that allows you to scan for specific address patterns. So you can tell the tool, for example, well, I only want to scan for IPv6 addresses that are employing, let's say, Realtek interface cards. And that has been, working for, quite a while, about 2 years. But we wanted to do things easier. So rather than, have you figure out what's the pattern, what we did is include a feature in the tool that automatically detects what's the address type, okay, and only targets those address types. So, for example, in this case, if I run the scan6 tool in this way, I just specify the domain name. /64 means a prefix. I'm assuming that the target network is a /64. What the tool will do is, first of all, map the domain name into an IPv6 address, okay? Once I do that, once the tool does that, it will analyze the v6 address and figure out if it's following any specific pattern. And if it does, then it will only target addresses that follow that pattern. So that's a way of, let's say, like reducing the search space when you are, or automatically reducing the search space of your scans when you want to scan a specific site.
But if you use the RFC 7 to 17,
you are dead. Yes. Yeah, I should say that. I mean, if you ask about that, I find it kind of like, let's say, nice when you find some sort of, let's say, vulnerable behavior. To fix it is nice, but to some extent, when the vulnerability is gone, it's like sad, so to speak, because it's, that nice stuff that you could, exploit, now you cannot exploit it anymore. So let's say that you have like about maybe a year or a couple of years during which you can, do this stuff. I guess that eventually, when that stuff, RFC 7217, gets widely implemented, yes, there's nothing else that you can do. And at that point in time, you will have to use something else, starting from, DNS mappings to something else. But you won't be able to do address scans as you are used to in before, okay? So this is an example. I will run it once I get rid of the slideware, because I'm getting this weird screen from OpenOffice, and the projector might not like my switching of screens. But what I'm going to show you later, hopefully, is that when you have, for example, different domain names that use different patterns, and you run the tool exactly in this way, in one case, the tool will target a specific address set, and in the other case, it will target a different address set. Side comment, if you want to try this on your computer, just add the -b, like for verbosity, so you will get the address range that the tool will scan, to double check, what's the tool actually trying to scan. Other related stuff. For example, the scan6 tool has, implemented support for extension headers for years. Actually, all of the tools that are part of the toolkit implement support for extension headers. But we have seen before that, they are widely filtered. So let's say that for some reason you want to use extension headers for, evading some sort of network control, but you want to actually, check that your packets are getting to where they want to get. The problem that I found when trying to do that was that all of the trace route implementations that I found, no one of them were supporting v6 extension headers. So there are, let's say, maybe 2, 3, 4 open source implementations of traceroute, but no one of them, at least 6 months ago or so, were implementing support for B6 extension headers. So what I did is I implemented this tool, path6, which is essentially traceroute, but since all the other name combinations were already used, that's why the name is path6. And what the tool does is essentially the same thing as traceroute, with the only difference is that you can request the tool to employ extension headers. So for example, in this case, you are just running traceroute against that address in blue, and by using the -u and 100, you are inserting a destination options header of 100 bytes, okay? And what you will see is that if eventually, the packets get dropped in the network, well, at some point in time, you won't get any more responses. But at times, you don't want to, let's say that you want to find where in the network your packets are being dropped. And, one possible way to do that would be to just run, plain traceroute for IPv6, of course, get the whole trace to the final system, then rerun traceroute, but with extension headers, and, compare the output of the let's say, of the two traceroutes. But at times, you want to be able to do that automatically. So that's why we produce this other tool, which is Blackhole6, which may sound like an attack tool, but it's not. What the tool tries to do is just find where in the network packets with extension headers are being dropped. In this specific case, what I did was to run the Blackhole6 tool against www.google.com, and the reason for that is that it's well known that they do drop packets with extension headers, and the extension header that we are using is a destination option header of 8 bytes. So what the tool will tell you is, well, what's the destination address and what's the corresponding autonomous system? What's the last node that responds when you don't use extension headers? If everything works well, it should be the same destination system. Then the tool will tell you what's the last node that responds when you use extension headers, and then it tries to figure out what's the system that is dropping the packets. So essentially, the tool is a script that uses the path6 tool. It obtains the output without extension headers, then it obtains the output with extension headers, then it compares the two lists, tries to find out what's the system that is dropping the packets, and then does some magic to obtain the information about the autonomous systems. In some cases there is some ambiguity, so that's the reason for which here when you see dropping node here, you get two possible, I don't know if it's in this case, but in some cases you might get like two possibilities. Or this could be this system dropping the packets, or it could be this other system. If you wonder, some of these tools, we created them and employed them to produce the test results that I was showing in the previous slides. Some conclusions before we get to the questions, I guess. This is a very, let's say, unpopular quote, but that's kind of like the way I think about this. If you think of, the internet in the 90s, where, you have all these issues with, source routing and all those, essentially buggy implementations, and you compare that to the B6 internet, it's kind of like the same state of affairs. Of course, you don't get very popular by saying this kind of stuff. Even more so if you do it in a, let's say, B6 related environment. But, I mean, being technically honest, I think that's the way things are. And I think, from my perspective, because I get paid for this, right? So it's nice, is that there's still lots of stuff to do on this. If you look at the implementations, there are lots of stuff that, still need improvements. There's also work to be done when it comes to implementations. Many of them are buggy in so many basic aspects that it's scary to some extent. And other stuff that I think there is to do is, to produce tools. There are only a handful of tools that you can use to play with IPv6. The first and probably most well-known tool is H2HC's IPv6 attack toolkit, which was, as far as I know, the first toolkit for B6 for, allow you to do anything that you want. Well, whether you should use one or another depends on you or on what you want to do. There's people that get really frustrated with the toolkit that I did because, well, they hear about this B6 stuff, So they want to, crash something. I don't know what they want to do, but they want to run a tool that does something that is nice. And they run the tool without any commands or just with a destination address, and the tool tells you that, well, there's so much stuff that you should have specified and you didn't, that the tool is not able to do anything. And people get frustrated about that. But it's nice if you are, testing your stack or things like that to have a toolkit that is flexible. I don't know if there are any questions. While you do it, if this works, it doesn't. Yes, go ahead.
Well, first, when I was studying about IPv6 a few years ago, the V6 version of the address resolution protocol was called Neighbor Discovery.
Neighbor Discovery, yeah.
I don't know if they changed its names anymore. So,
no, it is. It's still Neighbor Discovery, yeah.
But it seems to me that they seem to be vulnerable to the same kind of spoofing attacks that we had before.
Exactly, yes.
And no one's done anything about it.
Exactly, yeah. Well, actually, I mean, strictly speaking, if you wonder about that, there's something that was published on the topic that is called Secure Neighbor Discovery, which is called SEND. Now, there are essentially two basic problems with SEND. Three basic problems if you want. First one, Windows doesn't support it. So if you want to secure a V6 network, and if you want to mitigate the neighbor discovery attacks and you have Windows systems, it will be of no use because Windows doesn't implement it. Actually, I should double check, but I would say that it's likely that many, if not most, of the stacks, they don't enable send by default, okay? So that's one part of it. Second part of it is that it has at least a couple of patents, patent claims on it. So I recall, for example, there was people from the Kami project. Kami was the people from Japan that produced the V6 stuff for BSD systems. And essentially what they say is, well, there's no sense in us, spending time on this stuff because there are patents covering this and, we might get into trouble. Now, third problem is that essentially what SEND does, there are many details, but they don't matter that much. But what they do is they use a PKI, public key infrastructure, to sign, for example, the neighbor discovery packets without getting into much detail. Now, what's the problem with that? The PKI. So you need this, a certificate chain just to be able to sign the ARP packets in V6. How do you get the certificates to the clients? Blah, 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 blah. Painful. Yes, exactly. And the final one, which I think is yet another reason for which that didn't fly, is that there are so many other parts of the puzzle that need to be fixed that, fixing only that part. Just a simple example. Let's say that you have not yet deployed DNSSEC. So what's the point about, worrying that much about ARP if, the DNS part is still vulnerable?
But there is supposed to be a layer independence, okay? I think it's a little bit like what TJP said earlier today. Let's not fix this because that's broken. That doesn't make any sense.
I'm sorry. I'm not saying
no one fixes anything.
No, I'm not saying that the IETF didn't fix it for that reason. I'm saying that if you are an operator, if you are the guy running the network, given the tools that you have, it's like, it's like having a boat which has this big hole in here, and you just are taking care of, the pain.
I don't buy that.
But when it comes with the stuff that was produced by the IETF, in theory, there's something that was produced, but in practice, as you say, is to operate that from my perspective is a nightmare. And when it comes to neighbor discovery, it's a little bit worse than that. Because there are problems which it's not necessarily that they are worse in IPv6, but I can give you just a simple example. In a typical IPv4 network, let's say you might have, 200-something systems, because you have a slash, 24. Maybe worst case scenario, you have 65K systems, and not really. So, for example, if you have a data structure, such as the ARP table, there's an implicit limit because of the size of, of the before subnets. Maybe the implementations were crappy, but you could get away with this. Now, in V6, since the networks are way larger, now you don't have that artificial limit. And what's the stuff that many stacks have been vulnerable to? Well, they don't enforce limits on the neighbor cache. Yeah, and they exhaust the memory. Yeah, and it's actually even worse than that, because in many cases people assume that you can only exhaust the neighbor cache if you are a local attacker, because well, it's supposed to be layer 2, 3 stuff, right? Now think about this other scenario. You have a remote network here. I'm an attacker, and I'm just trying to scan your network. So exactly. So it's like I'm essentially triggering lots of neighbor discovery requests, and if the router here is not able, well, doesn't enforce limits on that, the network crashes. So it's funny, but in the manual page of the scan6 tool, we actually limit the packet rate on purpose, just to avoid you kicking the network out of, yeah. And we also say, well, be careful, because if you are interested in finding the systems, and if you do it like quickly enough, you will actually wipe the network away. So there's lots of that stuff. And the final one with neighbor discovery, which is, I'm talking about layering that you mentioned. From a, let's say, a theoretical point of view, that of doing the address mapping in ARP in IPv4 wasn't that nice, because you are running like a layer 2 protocol, which is ARP. It runs directly on, on link layer packets. In V6, they say, okay, let's do things a little bit nicer. And rather than using a layer 2 protocol, let's make everything in IPv6 run over IP, over IPv6. So neighbor discovery traffic is actually IPv6 traffic. Now, the problem with that is that you get extension headers, you get fragmentation, all of that stuff. Now, if you want to do any kind of, let's say, controls at layer 2, now you have to deal with all of these complex packets, which in practice you can't. So it's worse. Yes, from my perspective, I would say that, it's just, the network just has to evolve in the same way that it happened with IPv4. The problem is that
it seems to me that the IETF people are doing all the same mistakes over and over again. Don't they ever learn?
Well, I actually, in a different presentation, I had a slide that said this. So, and there's some truth to it. For example, if you check, let's say, the commit logs for open source implementations, you will find that the people that were actually working on the B4 code were probably very different from the guys working on the B6 code. For example, B4 code was done by the people at Berkeley in the 80s. Now, the B6 code in BSDs was done by people in Japan. So probably they didn't learn the lesson.
Very
But there's also stuff that is worse. Probably everyone here knows that source routing is ugly. It has been ugly for at least 20 years, right? It was formally, well, not formally, but in practice deprecated in the late 90s. So if you want to do source routing, you cannot do it in IPv4. But even then, it was, again, standardized and put into IPv6 in the 90s again. So it was deprecated for V4, added to V6. It was deprecated in 2005 or 2006-07. And now there's a company, which I will not mention, that has produced a new technology, which is, I will not mention what it's called, but essentially does source routing again, with a different name. They don't call it source routing because it sounds ugly, but it's source routing. So it's the same thing over and over again. Another example that I can give you, and this is being the last one because we're going to get killed here. In the 90s, for 80s, 90s, there were all these attacks based on predictable values, even in 2000-something. So, for example, you had predictable TCP ISNs, you have predictable IPv4 identification numbers, like dump scans and all that stuff. Then in 2000-something, when there was all this issue with the DNS cache poisoning attacks, we were discussing again port number randomization, okay? So same problem over and over again. If you have to use identification numbers, do something that is not predictable. You find exactly the same thing in all the B6 stack. Even an implementation that has fixed the B4 fragment IDs and they do randomization, they do predictable values for IPv6.
So as I said, going to IPv6 is kind of going back to the 90s.
Yes.
Pretty much.
With the threats that
I mean,
and with the threats that we do have today, because the attackers are the defenders didn't learn the lesson, but the attackers did.
Well, the nice part from my part, when it was in the 90s, to be honest, I didn't get that much to play with all those stuff. And I thought, it's sad that, there was all this stuff that was easy to exploit, but I wasn't able to play with. Well, you can do it now with B6. So that's what I would say. So it's like, you know...
And just to make it very quickly, the other question. So,
Yeah.
But I get the impression that the V6 is all about dressing, and they didn't bother changing TCP6 and UDP6 port numbers.
Exactly.
Yes.
Yes.
So they are very easy to scan. As well. They didn't touch the
B6, well, there's the unfamous quote that says that IPv6 is 96 more bits, no magic. So 96 more bits for the addresses, no magic. There's stuff, yeah, there's the packet structure that changes a little bit. Now you change the packet, and there's also, and I'm getting into very politically incorrect if you want, one of the first things that I read about V6 is that the packet structure was so wonderful because now you could expand the protocol in so many ways that you wanted. And so that of having a chain as opposed to some, small, small space for options was a good thing. Now, turns out that, extension headers is probably one of the most ugly things in IPv6. And you won't even get to, to work properly.
You have been mapping, using your tools to map the networks, the IPv6 network. I get the impression from the documents that one of the main reasons for IPv6 was trying to get rid of NATs. Did we get there?
Bullshit, I would say. Again, I shouldn't say this, but the idea is that the official story is that NATs are ugly because they break the end-to-end principle in the internet, right? And that comes...
To dream of absolute interconnectivity about everything.
Exactly. Well, I have and this is my last comment. There's an interview, you should watch it. An interview by David Letterman to Scarlett Johansson, right? I mean, if you don't care about what she says, she's pretty at least, right? And he asked Scarlett Johansson about, internet-related stuff. And so I call that the Johansson principle, right? Scarlett Johansson principle, in which she says that she didn't like that kind of connection because it was too connected, right? And that's the way I feel to some extent about, what IPv6 could, could result into. So I don't think if, let's say, from the 1980s point of view, it could be desirable to have everyone connected with everyone. But nowadays, you only want to be connected with the people that you really want to. There's all these people that argue, for example, that with the Internet of Things stuff, you want to have, your refrigerator, your TV, and all of that connected directly to the Internet. A couple of weeks ago, there was a guy saying that he wanted to have his, garage, the system that would open the door of his garage directly connected to the Internet. I think that lots of people are going to die if that happened.
But my question was of more experimental nature.
Yeah.
Are people deploying NATs in the wild or no?
Yes. Actually, there's there's Linux code for that. They ship with, yeah, exactly. But there's other stuff, and this is, so when you have NAT, you have two things. You have the address translation thing, which is that's why the NAT is called NAT. But then as a side effect of that, you have what some people refer to as a diodo firewall, which means that only outgoing connections are, allowed. Now, with B6, and I can give you a concrete example, Comcast, which is one of the, guys that are pushing, B6 deployment more, what they deployed on their customers' premises is a firewall device that doesn't really do address translation, but it implements a diode firewall. So they only allow outgoing connections. That means you are not doing NAT in the way that you know it because you are not, overwriting the addresses, but incoming connections are not allowed. And if I had to deploy... well, I have the B6 deployment at home, and that's what I do. And you have all these, some crappy devices that maybe they will never get updated when it comes to the code.
Yes, but I'm not talking about the diode effect of NAT. I'm talking about really rewriting the address, because this will break so many things. It will need all the re-implementation, everything, helpers, protocol helpers, and all this stuff.
It's being done. And actually, there's people that and that's kind of like to the limb. You should double check that. But I even recall talking with a company, and there's the PCI standard, and there was people that apparently they were interpreting the standard as saying that you had, in order to comply with the standard, you had to have a NAT in there. So I didn't, double check it. But there was people that was even interpreting nuts in that way. Another thing is that I think that from my perspective, B6 tried to do some things, try to achieve the same thing in a very different way. And I'm of the idea that, that's not the way humans work. I mean, you want to reuse the knowledge that you have as much as possible. So there's people, for example, that they are used to nuts. And not because they are pretty, maybe they use it because they need them, but when they move to IPv6, they want IPv6 to look as much as IPv4 as possible. And that's one reason for which they deploy B6 NAT. So it's something that is happening. The thing is that the level of deployment of IPv6 when it comes to customers is not so widespread to be able to tell or to say, well, NATs are being deployed with this percentage. But it is happening, yes. Okay, so I'll be around today and tomorrow. If anyone has questions, please, just drop me a note. So thank you.